Ready? Oh, okay. We talked about residual stresses, and they result from prior, actually I didn't emphasize yesterday, non-uniform thermal or mechanical loading of the material. If you heat things up uniformly or you stretch them uniformly, you're not going to introduce residual stresses. In fact, you tend to eliminate them if everything is uniform. But if you have temperature gradients, and it only takes about 300 degrees centigrade for most metals, or you beat on the surface or bend or something and then bend back, you will introduce non-uniform loads in the material, either thermally or mechanically, and that'll lead to residual stresses in the part. Those residual stresses might be either beneficial or detrimental. If you have surface compressive residual stresses, then that's going to be beneficial because those residual stresses add to the surface stresses, and in this case a negative added to the positive surface stresses means you're going to have better fatigue life, better stress corrosion resistance, and things like that. It's important in a lot of materials, not just metals. Window glass is tempered in certain ways that you can get compressive residual stresses on the surface. It's also chemically treated to do the same thing. And you can, I remember Professor Ullman used to have a piece of glass that was kind of maybe 12, 18 inches across, and it was bowed about 1 or 2 inches, and he could just put it on the table, just flatten that piece of glass. Okay, just press down on it, flatten it, it'd spring right back elastically. You wouldn't dare do that unless it had very significant residual stresses, compressive stresses. And he could do that because it had been designed that way to have the compressive residual stresses, and therefore it didn't fracture and cut his hand when he did it. Okay, today I don't have very many overheads, but I have a lot of touchy-feelies. We'll talk about a number of different things about how to fabricate materials. Now, we talked about fracture mechanics, and we talked about the fact that materials have flaws. All materials have flaws. Well, where do those flaws come from? When we're talking about metals, we're really talking about virtually every metal starts out in some way going from the liquid to the solid. It has to solidify. Even if you're making metal powders, you melt the powder, you melt the metal, and then you spray it to atomize it, and that's the solidification process. So you have to first melt the material and cause it to solidify. During the solidification process, there are lots and lots of types of flaws that can occur, and you've got a handout that goes through some of that stuff. There are lots and lots of different solidification processes. People have been melting metals for thousands of years, and they've come up with a number of different techniques. The simplest is just pour the stuff into a mold. So if this happened to be a mold, whoops, what's inside there? That's interesting. I didn't realize I brought that with me. You just pour the metal into a mold. When it's all done, hopefully you can get it out. Typically, the mold may have to have slightly sloping sidewalls. Actually, I guess I do have an overhead that I can show you of typical ingot casting technology, which was, they still do a little bit of this. About 2% of the steel is produced this way. All of the aluminum in the world is produced this way. This is ingot casting. And you have slightly tapered walls. This is different types of processes in steels. In this case, you get rid of all the residual gas in the steel. Over here, you actually leave some residual gas so the steel kind of foams a little bit. It's called rim steel. And the rim steel, you don't get as much solidification shrinkage. You actually have to cut off the top of this ingot, and that becomes scrap. Over here, you have to cut off the top third of the ingot. And I'm not going to go through it because it's a ship type of thing, but if you go to prior years, I spent about half a class going through the failure of a tail shaft in a liquid natural gas tanker, and it was because of this type of solidification defect that occurred before they forged the shaft for the propeller of the ship. So that's just very simply ingot casting. We don't use that as much anymore because you have to throw away about 25% of this, or not throw it away, you have to recycle scrap for about 25% of your material. Starting in the mid-60s, people started to do what's called continuous casting of steel. And I don't have a piece of steel that's continuously cast. Actually, virtually any piece of steel was originally continuously cast. But the typical casting size for steel, continuous cast steel, is like a 10-inch thick slab by maybe 4 feet, 5 feet, or actually maybe 4 or 5 feet wide typically. And I didn't want to bring one of those to class. Okay, but we do continuously cast other materials. This is a piece of continuously cast copper. This was some copper that was, it's got 0.1% silver in it. It was supposed to be for the overhead wire for the Northeast Corridor extension from New Haven to Boston of Amtrak. And this was going to be rolled down. I don't think I even have a piece, but I think my technician has a piece of. It gets rolled down and drawn into about a 5/8 inch diameter wire, and that's what the trolley or the train runs on. And the pantograph, which is this little electrical conductor pickup, a piece of graphite up there, slides along there at 150 miles an hour when it's going down the track, and that's how it picks up the electricity to run. This is basically continuous cast. You pour it in a mold and it gets pulled out the bottom. Actually, this is horizontal caster, so it gets pulled out the side. And every now and then you cut it off because in continuous casting of steel, people have run for a whole week before they ever shut the thing down. They just keep running 24 hours a day for a whole week. And if you actually calculated it, you'd have something that's a mile, several miles long, an ingot several miles long. But the advantage is you have no hot tops, you have no shrinkage from your solidification except at the very end of that mile-long thing. So you're just cutting things off as you go, which is another little trick, which I think I'd probably talk about cutting stuff. This is just a cross-section of the same thing. You can see the solidification grain pattern in that. It turns out that in general, you need a large enough original casting if you're going to work it down to a product. That was not used for the Northeast extension because you really needed, in general, something that's much larger in diameter. You need to, typically from a cast structure, to get a good wrought material, you need probably a 90% reduction in area, at least 80%. And they only had about a 60 or 70%. And for that reason and others, that product was rejected, and they went with a different supplier who had bigger casting machines. Actually, they had a different type of casting machine, to be specific. Because you've got to get rid of the flaws. Typical flaw sizes are on the order of some fraction, maximum flaw sizes in a casting, are some fraction of the size of the actual casting that you've got. So if I've got a huge casting, an ingot casting that starts 24-inch thick steel by 3 feet, 24, let's say 24 by 36-inch steel by 8 or 10 feet long, may weigh 20 tons typically for that steel ingot, and they're going to roll it into a plate. Typically for a 6-inch thick plate, if I remember I'm going to look at my notes, the largest acceptable flaw for a 6-inch steel plate, and that's used in pressure vessels and stuff, has to fit within a 12-inch diameter circle. 12-inch diameter circle, that's bigger than this. I could have a huge flaw as a lamination in that plate, because if I think about these types of defects here that might be in the casting, I've got to do enough rolling and forging of that to weld those things together, to close them up and weld them together. And in the welding course, you'll hear about what it takes, but typically it takes 80 to 90% reduction. And so people have been trying for 100 years or more to come up with better ways, reduce the flaw size. You can go to smaller castings, and one way to do that is to try to cast to a net shape. And you've seen this. This is just a brass model of an MIT ring that I got at my 25th reunion. This is the actual model. This was, I don't know, I think looking at the surface, this was probably sand cast. You'll see a very rough surface on the inside here surrounding the beaver. That's typical of a rough sand cast. So instead of a metal mold, which would be a permanent mold, because it has a permanent shape, and you pour the metal in the mold, you would basically make a sand mold and use some glue to hold the sand together, and pour the metal in. That's how they make cast iron engine blocks. It's all sand molding. It's all automated in this country, but you end up this very rough surface, and then you can polish it up, obviously. This is lost wax casting. We talked about that. You start out with a plastic wax model, and you dip it in a slurry, and you keep on putting more and more ceramic slurry around this, and eventually you end up with a mold. You melt out the wax and pour the metal in. So I'll pass these around. I'm not that concerned about that, but I really do want the gold one back. But you can look at the difference in quality of surface finish. This one actually, I think I may have mentioned, one of my classmates lost his, and I had lost mine a long time ago. So we actually got a classmate who used to only wear his when he went to Asia, because this has a lot of name recognition in Asia, not as much in the United States. But he used to only wear his brass rat when he went to Asia. So we took it to a dental jeweler. My classmate took it to a dental jeweler, and we had some new ones cast. And that's only, actually, that ring is less than a month old. Okay, but no, I didn't make extras of that, because in that case the dental jeweler was charging me for the gold content. And you know, back when I was a student and I could kind of come up with palladium at 50 bucks an ounce. In that case, gold at $400 an ounce, that cost me 1,200 bucks for that ring. Which is why I just didn't get it back. Although I do still have a spare, because I had the brass rat from before. So I do have a spare. So you can have ingot casting, continuous casting, permanent mold casting, sand casting, die casting. Die casting, you just take a piece of metal and you machine out a cavity, and you put two halves of this thing together, and you squirt typically low melting metals like aluminum or zinc in there, just like you injection mold plastic. You just squeeze it in like you're squeezing it out of a toothpaste tube into the mold and let it solidify. And since it's a permanent mold die, you can do this fairly quickly. So you can pop out parts, and you have automatic machines that bring the dies together, squeeze the liquid metal in, hold it for a second, water-cooled metal molds, hold it for half a minute or a minute, depending on the size of the part. Open up the die halves, the part drops out. You may have little ejector pins to push it out. It falls down into a bin, the molds come back together, and you start the process again. So that's die casting, typically sometimes used for copper alloys. People have tried to do it for steels, but they don't have mold materials that can take the high temperatures and take the thermal shock. A lot of thermal shock when you put molten metal into a metal mold, even if you preheat it. And so you're dealing with steels at 1500 centigrade. They've tried molybdenum alloys and things over the years. If you could come up with the mold material, you could make a fortune by die casting steel parts. But no one's been able to do it. And they've spent millions and millions of dollars. People have tried to, when you want to make sheet material, people have tried to cast it thinner and thinner. If you're making plate, yeah, you want to start with a 10-inch thick ingot. And I think I showed you once before the chaparral steel, the continuous casting, the I-beams, the dog bone shaped I-beams. And those are probably 6 or 8 inches thick, but they were dog bone shaped. Well, if you're going to make sheet material to get 90% deformation, you don't need to make it 10 inches thick, although the integrated mills do start with 6 or 8 or 10 inch thick and roll it down into sheet. People have tried to cast 1/8 inch thick sheet and have spent hundreds of millions, if not billions of dollars trying to develop that, because you would save a lot of money. One rolling mill in a big integrated steel mill is about $600 to $800 million just for the capital investment. So you could save yourselves $500 million in capital equipment costs if you start out with something thin. They have actually cast, this is about the only product that's commercially available. This is amorphous metal sheet, and it was developed by what used to be Allied Signal, now a part of Honeywell, but developed in the 1970s, and you basically squirt the liquid metal onto a water-cooled copper disc that's spinning at about 60 miles an hour. And if you do it properly and you have all your fluid dynamics controlled, you actually cast it. This is a cast structure, except it's solidified on that water-cooled copper at about 1,000,000 degrees per second. And therefore this, be careful, turns out to be very strong. It also is fairly expensive, on the order of about $10 a pound, so you can't use it for other things because the dies wear out or the molds wear out and things. And you can't make it but so wide. But it's extremely strong, but it's amorphous. It has the structure of glass. It is non-crystalline. And that gives it very interesting magnetic properties. For example, I brought this piece with me. This is one of the products that's made with it. This is a little soft magnetic yoke. One of the largest applications of this material, you ever gone through the video store, and if you buy a video, they have to take off this little tag, or they have to rub it over this thing before at the checkout counter. What they're doing is they're demagnetizing a strip of this that was inside that little plastic thing that was attached to it. So they have a demagnetizer there. If you want to steal things, if you're a pickpocket, you have to just bring your own demagnetizer into the store, and then you can go through the gates. But basically, just like the security at an airport is using eddy currents to try to pick up a magnetic signature, this material, with the proper composition in amorphous form, has the softest magnetic properties of anything in the world. It is unique. And therefore, you can set that eddy current detector, and it's not going to get set off by someone's keys or anything they've got in their pocket, unless they happen to be carrying something like this, which is the product that comes out of this. This is a magnetic yoke. One of these has to go into every computer, basically as a surge protector for the power coming into the computer. If you get a high current go through this, you just put the wires through this, and if a high current tries to surge through there, then the soft magnetic material will create enough inductance to take the spike out of it. Be careful of this stuff. It has if you measure it, it has about 500,000 psi strength because of the amorphous structure, and therefore you can get a real paper cut here. Okay, seriously, it's worse than most paper cuts. It'll go fairly deep. Okay. But it's not that bad, just as long as you're aware of it, just like any paper cut. I mean, it's dangerous to handle paper. You can bleed, right? Well, you can bleed if you handle that as well, but I don't think it's so unsafe that we can't pass it around. Plus, I have Band-Aids downstairs. So there's also newer techniques. The newest technique is various forms of solid freeform fabrication. What this is something made by 3D printing. Professor Seema gave me this. This is a little toy, and they made sort of a mini, it's not really the Taj Mahal, I don't think, but anyway, and a couple of the spires have broken off over the years as it gets handled. But basically, in this case, it's ceramic powders, and they just have an inkjet printer that goes along and squirts out a little slurry of powders in a liquid, but only puts them where you want, and they actually call it 3D printing. They put down a layer, and then they print another layer, and another layer, and another layer, and you can make near-net shaped parts, you can make them out of metal powders, but then you have to heat up the metal powders, sinter them together to make a solid object. So that's called solid freeform fabrication. It's been used with metals, and I have 2 examples made in my own lab. This is basically just an Inconel 718 that was electron beam melted back and forth. You can see the different texture on the surface, and just laying down a little wire and melting it, and just back and forth, like the raster on a TV screen, and you can make up a pad of material. This happens to be a circular part where we were trying to build up a bronze alloy such as the Navy might use for propellers. If you look at the side, you can see the electron beam melting here. What's the advantage of this? The defects are smaller. If the maximum flaw size is proportional to the casting size, I'm casting, each little casting is just a little bead here that's not much bigger than a ballpoint pen tip. So the flaw size should be very small in these things, and in fact it is. It also solidifies rapidly. You can get interesting microstructures and properties from something like this. The problem is residual stresses, because I got tremendous non-uniform temperature gradients. And in fact, typically when you build up something this big, it's going to crack on you. And so the trick is, how do you resolve the residual stress problem in these things? One way to resolve the residual stress problem is you lay down the material at 1,000 degrees centigrade, so it's stress relieving itself as you're putting it down, except that kind of makes things a little bit messy. But people do that. There were some other techniques that we were looking at. So that's basically kind of a very quick overview of casting processes. You've got to solidify your material in some way, but solidification inherently will leave blowholes, voids, cracks, and you've got to get rid of some of those things in many applications, not in every application. Hey, you can cast an engine block and it can have pores in it 1/4 inch in diameter. As long as it's not in the cylinder bore where you're trying to machine, you don't really care, as long as it doesn't, as long as it holds the oil and water pressure inside the engine. But there are other applications where things are critical. I didn't bring a forging. I had enough weight today to not bring a forging. But one of the things we do is we basically just heat the material up and we squeeze it, just like you knead dough, if you will. You squeeze it together and you forge the material. This actually is a forging. This is a copper forging. This one actually is forged in a circle, and the properties, the radial properties of this are very important, because this is the part for a shape charge projectile, basically an artillery shell. Okay? And basically what you do is these little indents here are going to take the explosive, and when you set off the explosives, they've known this for 60 or 70 years, you basically invert this little cone. The explosive that being out here basically takes the cone, which is shaped this way, and folds it back on itself. And so as it folds it back on itself, all the material on the outside kind of converges to the inside. And as it does that, with the energy of the explosion, you generate a lot of heat, and you end up shooting out a jet of molten copper. This is called a shape charge. Okay? They actually use them in construction. This is not just for military purposes anymore. That jet of molten copper might be 2 feet long. You have to go to pretty high-speed photography to see all this, because it's basically as the explosion is going on. And that jet of molten copper will cut through 2 foot, if it's a 2 foot long jet, it'll cut through roughly an equal thickness of steel. So just go right through the old-fashioned armor. So people now have ceramic armor because it won't cut through ceramic, it'll only cut through steel, because it embrittles the steel as a molten copper. But that's a forging. And the properties of that are critical, because everything's got to be symmetric. As the charge goes off, if the things aren't symmetric, your shape charge is not going to be heading in the direction you want. But they actually use shape charges to cut pieces of metal in the field sometimes. As long as you're someplace where you can set off explosives without people getting upset. But they also forge much larger things. Some turbine blades in the old days were forged rather than cast. The reason most turbine blades today are cast is because the alloys, the high temperature alloys, can't be forged. They've got such high strength at temperature that they're not forgeable. And so they have to be cast. But then they grow them by directional solidification and sweep all the defects and pores ahead of things. There's 2 basic types of forging. The largest manufactured metal parts in the world are basically open die forgings. And I thought in this thing, yeah. Here's a picture of an open die forging in a steel mill. There's a person standing here. There's the ingot. This is the clamp that holds the end of the ingot. This is one of your larger ingots. This one's about 4 feet high by 6 feet by maybe 10 feet. This one may weigh 100 tons or 150 tons. The largest ones actually weigh 350 tons, the largest ones in the world. They're produced at 2 plants in the United States, one at U.S. Steel and one at the former Bethlehem Steel plant. It's the only part of the old Bethlehem Steel plant that I believe is still in operation. These facilities were built before World War I to make battleship gun barrels. And to replace those facilities would probably be $5 to $10 billion in capital equipment. That's why no one else is going to build any of these. But the United States can make the world's largest generator rotor forgings for electrical power generation. So in the really big version of these things, open die forging, you got a press here, which is a great big hammer, comes down and beats on this hot piece of steel, and you can rotate it around, and you take that square, that rectangle, and you turn it into a circle, just kind of by beating on it. You know, it's like an old blacksmith used to do with his hammer. He'd take a rectangular piece of steel out of the coals, and he would just rotate it and beat on it and turn it into a circle. Well, this is just a bigger blacksmith, if you will. Yeah.
Did you say the biggest one weighs?
350 tons, 700,000 pounds. They can only produce about 12 of those generator rotor forgings per facility per year. This is another picture shows you how they rotate it. It's just a big chain. There's a person standing down there. These are not the biggest ones, but you can make all kinds of shapes. Okay, that's just taking some out of the furnace. Okay, but it's fairly large facilities. Now, there was this set of defects. These are typical defects in the microstructure. They actually had some pores, and this is cracks growing from the T-cracks growing from the pores. If you want to know the details of one of those that tail shaft fracture, you can go to one of the earlier web things from last year in 337, because it's a ship failure, and I'm not emphasizing ships in this year's version of 3371 lectures. But if you're really interested in seeing that type of stuff. But they forge smaller things. They have what they call closed die forgings. A closed die forging is just like the die that you have for solidification of die casting, except in this case you want to have good impact strength in your die, because you're going to put a piece of hot metal in a closed die which has the shape of what you want. Before, you just had, it's like a hammer, you know, flat edge of a hammer, and you turn something into a circle by just going around and making hexagons and octagons and start approximating a circle. In a closed die forging, you actually machine the shape of the part you want, and you put the hot piece of metal in there, and you come down and just smash it, okay, in a great big press. This is medical scissors. This is one side of a medical scissor. This one actually has the insert brazed on that we talked about before. This is the cobalt alloy insert brazed on, and they're going to grind that, and that's one half of the scissors. Well, it's expensive to make these. Most of this work is now in Pakistan because you've got inexpensive labor, and it's a lot of hand labor putting hot pieces of stainless steel into a little forging press. There are bigger forging presses. The largest two in the United States were built just after World War II in the 1950s. One of them is right out here in Worcester, Massachusetts, actually North Grafton, at what is now part of Krupp Steel Works, a German steel company, but originally it was what's called Wyman Gordon. It's a 50,000-ton press, and they can take parts that are half the size of this room and forge them. It's a pretty good sized press. I mean, the press I showed you before where they were forging the stuff at Bethlehem Steel is small compared to the Wyman Gordon press. The Wyman Gordon press, the base goes 6 floors into the basement. Okay? It's got a foundation that is concrete and steel that goes about 6 stories deep. And up above, it's about only 4 stories up above, but it's a good sized machine. They had a crack in one of the beams. They had to re-weld a few years ago, so I got to go down there and help them figure out how to re-weld it. The beam was 10-inch thick. The web of the beam was 10 inches. The height of the beam was like 13 feet or something. But in order to, they had estimated a replacement cost of that forging press 10 or 15 years ago of $2 billion. For that press. There's one in Cleveland and Alcoa where they forge great big aircraft parts, and there's the one at Wyman Gordon. And supposedly the former Soviet Union has a similar size one. World's largest forging presses. The Air Force in the 1950s originally was thinking about building another one. but they couldn't afford a foundation, so they were going to use a granite mountain in Colorado, okay, for the foundation. This is an attempt to get around the cost of the forging dies and end up with something a little closer to near net shape. This is basically laser cut out of stainless steel plate. They don't use that. They still use the forging because it went to Pakistan where it's cheaper. Yep.
This is two different materials then?
This one is two different materials. You got a cobalt piece brazed in there, so that one's partially processed. They didn't forge it with that piece in there. Yeah. Okay, they actually forged it and then they machined it and brazed the piece in. It's just a little bit further in the manufacturing process. Another thing we tried was to see if we could take wire or rod, just bend it and weld it. This one hasn't been welded, but weld it in a spot welding machine and see if we can make a preform for scissors that way. A lot of hand labor in scissors, particularly in making the thumb hole or the thumb and finger holes, because you got to get in there and sand that. And used to do it down here in New Bedford with American labor, but couldn't survive the labor costs in the United States. I passed around the thing that was a cast thin sheet. You already saw this. This is the I think it's Nippon Steel. Two-layer sheet with some plastic in between for sound deadening. This is expensive because you have to roll the sheet very, very thin. And to roll the sheet very, very thin creates a lot of problems. You've already seen this, so I'm not going to pass it around. It turns out that if you just try to roll a piece of material in a rolling mill, the thinnest that you can get is about, if this is the roll radius and this is the thickness, T over R is going to be greater than 1 over 500. And the reason for that is it takes some force to roll the material. This is if you're doing cold rolling, okay? And you put typical types of yield strengths of materials and you put typical moduluses of elasticity in here, you're going to find that the roll, well, I guess I drew it well, flattens out. And so you can actually bring the roll gap down to 0 where the rolls are touching and put something through there, and because the rolls will flatten under the force, you won't exceed the yield strength of the material when you get to this type of ratio. So if I want to make, just think of this ratio now, if I want to make something that's 2 mil foil, the largest size diameter roll I can have is 1 inch, right? 2/1000ths of an inch thick, then 2 over 1 inch is 1/500th. And that means that in order to roll very thin material, I have to have very small rolls. Well, the problem with very small rolls, if it's going to get very long, it gets nice and slender, and then the roll's going to bend. I lose all the stiffness in the roll, so I have to back it up. So I back up those 2 rolls with these 2 rolls, and typically on larger mills, you basically just put 4 rolls together, and you'll have what they call a 4-high mill. This is the work roll, and this is the backup roll. So you got 2 backup rolls and 2 work rolls. The sheet of the plate goes through here. That's fine for a 2-inch plate, 1-inch plate, 1/8-inch steel, okay, and things like that. You can figure out what the roll diameters are from this. But when we go down to foil and try to make something as thin as the sheets that are going to be, sandwiching the plastic in something like this, you got to go to what's called a Z mill. After a Czechoslovakian, I can't spell Senzimir, Sendzimir, okay? Sendzimir, okay? Senzimir, S-E-N-D-Z, okay? Here, let me rewrite it. S-E-N-D-Z-I-M-I-R. A Senzimir mill, okay? For the guy who invented it. And it actually has 4 levels of rolls that get larger and larger just to back up the rolls, the work rolls. You end up with this a ring of 4, a ring of 3, a ring of 2, and then your work roll in between. And all of this is just to back up that little bitty work roll. Typical Z mill might have 1/2 inch or 3/4 inch diameter work rolls. It's just a little thin piece of steel. You can have Z mills that are, you know, this wide. They're cheap. They're only $5, $10, $25 million for the capital equipment. But if you want to make metal foils, that's how you have to do it in a Z mill. And it's kind of interesting to see how they work. So we've got forging, rolling to get rid of these defects. Yep.
What about just like aluminum foil, like
yes, they don't use, good point. Except for aluminum foil. Aluminum is soft enough and has low enough, they actually do something like this, only they do what they call pack rolling. They just lay up sheets. It's like taking a ream of paper and putting the ream of paper through the mill. Now you can do that because aluminum has this surface oxide that keeps it from welding the sheets together. If you did that with a bunch of sheets of copper, you just end up welding all your sheets together, okay? But it's called pack rolling, and it's only done on aluminum, and it is the reason why aluminum foil is so cheap, because you basically can do it on a cheap mill, roll, you know, multiple things. Remember the chaparral steel where they put 4 rebars through one mill? Well, in this case, they're putting 100 sheets or whatever in a pack roll through one mill, okay? So, and as you do it, you may get different sheet thicknesses on the top and the bottom, and you kind of segregate them, and aluminum foil comes in different thicknesses. So it's a good point. Thanks. You have to do something else for something as cheap as aluminum foil. But not most materials cannot be pack rolled. It just has to do with the surface properties of that aluminum. Anybody know how Reynolds aluminum got started? We mentioned that Alcoa got started by Charles Martin Hall, who invented the process to make cheap aluminum, right? And that became Alcoa, and then Alcan got spun off. And Péchiney in France was Hérault, who independently did the same thing as Charles Martin Hall. Anybody know how Reynolds aluminum got started? Ever heard of Reynolds Tobacco? Reynolds Tobacco, R.J. Reynolds and Company. R.J. Reynolds out of Richmond, Virginia. They needed aluminum foil to wrap the cigarettes, so they started an aluminum business to make their foil. That's why you have Reynolds aluminum, which kind of grew a little bit bigger than, well, it didn't grow bigger than R.J. Reynolds Tobacco, but it got to be comparable in size, let's say, a multi-billion-dollar business. Okay, so we can forge things just squeezing them together in dies or open dies, try to squeeze these casting defects and get rid of them. We can roll the material, but that kind of leaves us with either plate or sheet. We can, or actually can leave us with rod too. Okay, you can roll the material and make rod. But you also, you don't always want to change the shape of what you got. So there's one other process called hot isostatic pressing that was invented about 1948 or so at Battelle Memorial Institute. And until about a year ago, we had a hot isostatic press in the room right beneath us here. And I remember showing Professor Grant, who's well into his 80s now, that new isostatic press that we had about 1985 when we got it. And he says, you know, he had one in that same room in 1950. It was the second one in the world. Okay, the first one was at Battelle Memorial Institute. But a hot isostatic press is nothing more than a pressure vessel, a big pressure vessel, that will take, well, the one we had would take 30,000 psi. So you'll have this is your pressure vessel. You'll have a top closure, typically threaded in, screwed in, and then you have big, heavy, thick walls. And you can put argon gas in here and typically go up to around 30,000 psi. There are some that go to 45,000. There's some that only go to 15,000 psi. But you put the whole thing in, you either heat it internally with the heating coils in here, which means you have to have electrical feed-throughs, or you heat it externally, in which case your pressure vessel has to be able to take the temperatures. But the one we had would go to 2,000 atmospheres, which is 30,000 psi, and about 2,000 degrees centigrade if we use the graphite furnace. So you basically can forge the material and close up those defects in those pores without changing the shape of the material, because you're doing it isostatically. The pressure is uniform in here. You've got a gas surrounding it. So if I have a complex shaped part, okay, in here, the gas just squeezes it at high temperature. It's like forging it without changing the shape. You're just pressing it, and the high temperature is allowing the metal to creep and deform. A typical cycle on this on a big commercial unit, how big is a commercial unit? Well, a commercial unit, the vessel is about 300 tons. The diameter inside is about 5 feet. The height might be 20 feet for the whole vessel. Okay? You can put great big generator rotors for jet engines in there, and basically you can cast them out of materials that can't be forged regularly, and you're not forging it and by lots of deformation changing the shape, but you just squeeze those casting defects right out of it. So the pores that I showed you before over here from this this propeller shaft, those little voids in the casting just get squeezed together. Typical cycle might be day and a half to heat this thing up and hold it at temperature for 10 hours and then cool it back down. The walls of the one, there used to be one that was about this size, actually 64-inch diameter, a little bit, 5.5 feet, were about 10 to 11 inches thick. It was right up here in North Andover, Massachusetts, and about 4 or 5 years ago, it blew up one Saturday night. And there was one the largest piece that was left over was a 16-ton piece found a quarter of a mile away. Okay? Just flew through the air. Nobody got hurt. Although the operator, it broke up into about 70-some pieces when it let go, because it had a little stress concentration on the outside wall. Little stress concentration. It had a change in shape here. They made it a little bit thicker because of the threaded connection here. And it had a change in section. They had a fatigue crack grow there, okay, right there. And it grew to only about 5/8 of an inch in size. So you go through the fracture mechanics on this. It turns out because the material didn't have the proper toughness from the steel mill. It was much more brittle than they thought. It turns out the crack was assisted in growing because they cooled the outside and the water treatment packed the steel. It was a combination of factors. The way it had been designed, they should have had a critical flaw size about 6 inches in diameter before the thing would blow. When it actually went, it was probably on the order of ½ an inch in size, the critical flaw. No one was looking for such a small flaw because they thought they had plenty of toughness and they didn't know that they had this serious water chemistry problem. So there are multiple reasons why the thing went, but when it blew and you've got you know, a significant volume of argon at 2,000 atmospheres, it tends to, well, it kind of destroyed the building. There were about 70 pieces. They averaged about 4 or 5 tons a piece. One of those 5-ton pieces landed and crushed a folding chair that the operator had been sitting on about 15 seconds before. He had just gotten up to change the chart paper for the temperature recorder, and he was about 4 feet away from it when the thing blew, and this 5-ton piece crushed the chair that he'd been sitting in. He was sort of rattled by the event. He didn't die. It missed him by a couple of feet. You know. Oh well, this part of the building he was in was about 75 yards from the actual explosion. It was the outside warehouse type of building that the roof blew off and the crane, the 100-ton crane, got knocked off, and the actual little building where he is, actually there was still a roof above it and stuff, except for where the part came flying through the wall, knocked down the wall.
How heavy were the pieces that were flying?
2 tons. No, 4 tons. Sorry, about 4 tons.
How heavy is a car?
Yeah, 2 tons. These are about twice as heavy as a car. If you want to see, I got pictures of all the pieces. Maybe I'll bring in a picture book and you can see the pieces next time. But you can use fracture mechanics to do it. Now, at the time, this was the world's largest hot isostatic press. And it was critical. It was the critical path for making turbine discs for jet engines. And it was gone. And it takes about 3 years to build another one of these. Okay? It's not exactly something you go to a hardware store to buy a pressure vessel like that. However, fortunately, they didn't have to quit building jet engines for 3 years because there was another one that was about to come on stream out in Oregon 2 months later. But if there had not been, there would have been some real business interruptions, okay, in the jet engine business. But so far as other things, anybody ride motorcycles? Nobody's a motorcycle rider? If you ride a Harley or whatever, you're actually sitting right on top of that cast aluminum cylinder of the engine, right? Pistons going back and forth. You're sitting right on top. It would really be a bad day if that thing blew apart. And so they actually hot isostatically press those. They're aluminum castings with all the fins to cool. They're air-cooled engines, right? And it has all these aluminum fins. Well, you don't want to trust an aluminum casting. This is sort of a critical, you know, a safety critical part. So you hot isostatically press it. But if this thing takes a 24-hour cycle, it's about $1,000 an hour to operate one of these things. So to load it up, it's $24,000 just for this one step in the process. So you've got to put reasonably high value added parts in here. This is aerospace or safety critical motorcycle parts. Okay? You ever go price a motorcycle? What's a Harley selling for right now? 15 to 20,000, right? You say, I could get a small car for that. That's true, but they don't hot isostatically press the car. Any part anyway. Actually, there may be a couple of little engine parts, possibly, but I doubt it. I think most of them they figured out casting technology. Okay, well, we haven't finished all the deformation stuff, but I'll bring some of these parts back again tomorrow, or not tomorrow. We won't do it tomorrow. We'll do it on Tuesday. You can have Monday off. What a deal.